Hi all, now we are going to discuss on a sequence control of AC voltage controllers. So this is being employed for the improvement of the system power factor and for reducing the harmonics in the output voltage. So here you will be using two stages of voltage controllers in parallel for regulating the output voltage. So earlier we were having only this circuit, that is one set of thyristors which are connected anti-parallel and is connected to the load. And here sequence control means we are trying to employ more number of stages of voltage controllers and they are triggered in a proper sequence one after the other so as to obtain a variable output voltage with low harmonic component. So this is the first voltage controller and this is the second voltage controller and they are connected in parallel, and the sequence at which the thyristors are turned on are in such a way that you are able to get a variable output voltage. And now in this section we are going to discuss sequence AC voltage controllers with a resistive load. So that means the current and the voltage will be in phase with each other. Now for AC voltage controller we will be using a transformer which is having two secondary windings. That is, the primary of the winding is this one and you are having two secondary windings. In that the voltage V1 is equal to Vm sin omega t and V2 is equal to Vm sin omega t. So therefore the voltage which is coming across the thyristor set T3 and T4 is nothing but Vm sin omega t, and the voltage which is coming across T1 T2 thyristor set is 2 Vm sin omega t. That is, from this point and this point it is added together and that entire voltage is coming across the thyristor set T1 and T2. So effectively I can say that the sum of the two secondary voltage is nothing but 2 Vm sin omega t across T1 and T2 and Vm sin omega t across T3 and T4. So for obtaining the output voltage control from 0 to the RMS value of V, you will be controlling thyristor set T3 and T4 because the maximum voltage is V. Now for controlling the voltage from V to 2V is made possible by controlling the thyristor set T1 and T2. So for controlling the output voltage from V to 2V, you will be keeping the firing angle alpha for T3 and T4 to be 0. For T3 and T4, you will be keeping the firing angle alpha equal to 0. And firing angle for T1 and T2 is controlled from 0 to 180 degree in order to get a voltage variation from V to 2V. Now we will see this concept with the help of the waveforms to understand sequence control of AC voltage. Now in order to get the voltage variation from 0 to V, I am using thyristor T3 and T4 and the alpha for T3 and T4 are being controlled. Therefore effectively I can say the voltage which is appearing across the thyristor T3 and T4 is nothing but Vm sin omega t, and this voltage is being controlled. So therefore I can write the RMS value of output voltage V0 RMS is equal to 1 by pi integral alpha to pi Vm square sin square omega t d omega t, the all raised to 1 by 2. So during that particular period of time, the thyristor T1 and T2 will be in the off state. You are not controlling T1 and T2. So it is basically an AC voltage controller with operating thyristors T3 and T4. Now, when both set of thyristor pairs T1, T2 and T3, T4 are in operation, then alpha for T3 and T4 will be 0 and alpha for T1 and T2 are controlled from 0 to 180 degree in order to get the voltage variation from V to 2V. So from 0 to V, you are controlling the T3 and T4, T1 and T2 in the off state, and for getting voltage variation from V to 2V, all the thyristors are in the on state with T3, T4 with firing angle 0 and T1, T2's firing angle is varied from 0 to 180 degree. So the variation of the output voltage from 0 to V and T3 and T4 is a basic explanation of a full wave voltage controller with a resistive load. So therefore, we will be discussing with alpha varied for T1 and T2 in order to get the voltage variation from V to 2V. So this is the waveform which is corresponding to V2, that is Vm sin omega t, and this is the waveform corresponding to V1 plus V2, that is 2Vm sin omega t. So therefore we can say that it is directly the double because we are considering SI in turns ratio for the both set of the transformers. Now the thyristor pair T3 and T4 is always on, that is alpha equal to 0. Therefore the waveform which is corresponding, that V2, will be coming across the load till this point, and at the point alpha I am going to trigger the thyristor T1. So therefore the voltage goes up to the V1 plus V2 value. It will continue to conduct and therefore the output voltage will be coming across the load. And once it reaches an angle pi, the thyristor T1 is commutated because it's a resistive load, and we are giving the firing pulse to the thyristor T4 at alpha equal to 0. So therefore it will again start to conduct like this, and again at an angle alpha I am going to trigger the thyristor T2. Therefore it will go to the next waveform of V1 plus V2. So that negative voltage is going to appear across the thyristor T4 and turning it off. Now the output voltage will be like this. Again at 2 pi, thyristor T3 is turned on, so it will be following this curve, and once it reaches again at alpha, thyristor T1 is turned on and it will continue like this. Now we will plot the current waveform. The current will be having, so the magnitude of the voltage over here is root 2 into 2V, and magnitude over here it is root 2 into V. So therefore now we will plot the output current waveform following the same sequence, because the resistance and the resistive load, and therefore voltage and current will be in phase with each other. So this magnitude will be 2 into root 2V divided by R. So the complete set of waveforms along with the thyristors which are turned on at each instant is shown in this particular figure. Now we also need to write down the basic equation for the RMS value of output voltage. So V naught RMS is nothing but, we need to consider only a half cycle, that is up till pi. Why? Because we are squaring the waveform. So it is 1 by pi 0 to alpha. It is Vm sin omega t waveform. So it is Vm square sin square omega t d omega t plus alpha to pi, that is this period, alpha to pi, it is 2 Vm sin omega t, which is appearing across the load. So therefore 2 Vm is squared, so it is 4 Vm square sin square omega t d omega t, the all raised to 1 by 2 because it is root of the mean of the square. And this is how you can obtain the RMS value of the output voltage. So with this we are coming to the end of the 5th module. So we have discussed about the pulse width modulation index, then AC voltage controller, and finally ended up with sequence control of AC voltage controllers. Thank you.